Hello, IBA Karachi. Hi. Okay, we are all assembled for the last lecture of Beatriz. Yeah, we are completely on time. So over to you, Beatriz, to conclude things from the last lecture, maybe some computational aspect. So this is a tutorial. So thank you, Beatriz, for your continued support to introduce this exciting area of uh, chemical reactions and algebra associated to these things. Okay, would you like to conclude the last tutorial now?
Thank you. What I have planned for this tutorial is, well, it has two parts. So first part, I'm going to show you this tool, which is not very complicated, but I will show you anyway. And then I'll go over some of the concepts from the last lectures. And I will just let you think of some of the concepts and theorems, and maybe I will try to decipher for you the two theorems that I talked about yesterday, because I know they were too fast. So let me start with this CRMT. CRMT is chemical reaction network theory toolbox. And one can go to the webpage of Feinberg at the Ohio State University and download the tool. And maybe I will share the tool with you first and show you how it works.
Beatriz, are you taking us to the Messi program? Messi program by Alicia or something else?
No, I'm taking you to this Feinberg tool. So let's see if I can show you. I hope it works. Otherwise, I'll share the whole. So this is the tool, and here you can create networks. So you can give names to the species. And here, yeah, if somebody wants to download the tool in the meantime, feel free to do so. I will just create a few networks. So maybe I create this key network that I proposed for the first tutorial. So I will need this stick and these species. The species are created here. And two more species. And then once I have the species, I can create the networks. So I'm just copying the third network from the first tutorial. And it has these three reactions. And now I can save a network. Well, I don't think I even need to save. I can ask for a report. And first of all, I ask for a basic report. And a basic report has the following. It gives me the network. It tells me the number of complexes, the number of linkage classes. I remind you this was the number of connected components of the graph. Terminal, linkage classes. This is things we have not covered in the course, but if you're interested, there are references here also. The rank of the network is 2. It computes the deficiency. So the deficiency is 1. And then it gives me a short analysis. So it says as it has deficiency 1, then it is a candidate to apply deficiency 1 theory. I didn't talk about deficiency 1 theory. I talk about deficiency 0 theory. But there is also theorems for deficiency 1 networks. And then it explains to me what this theory says. And the best thing, it gives references. So this tool can show you some of the things that can already be computed for reaction networks, depending on some features of the network, and can lead you to some references if you want to learn more. So now if you want to learn about deficiency 1, you can go to these references. I can, once I have this basic report, I can ask for more reports. So it has deficiency 1, I can go to the deficiency 1 report. And then the deficiency 1 report tell me that using deficiency 1 theorem, it can conclude that this network cannot admit multiple steady states in a positive steady state class. So for no reaction rates, there are multiple steady states. So it's monostationary. And it gives me the references. So the theorems that are used here, I can find them. There are more reports on injectivity, for instance. It can tell me if it's injective. It is injective in this case. Again, it gives references. So it's not that all developed theory is here, but there are some things that you can find. There is something called concordance. You can also learn about this. It tells me about the degeneracy of the network. And it even lets me download the LaTeX code for the ODEs. So I can also get the ODEs from here. So maybe I show you one network. I need to here. For instance, I have the two-site phosphorylation. It's this network. It is very similar to the fourth network that was in my first exercise in the first tutorial. So this network in the first tutorial, it had one substrate, one enzyme. Then together with an intermediate, the substrate got phosphorylated. And then as a second connected component, it had the reverse process using another enzyme. Let me show the report because we can then see the network more clear. Yeah, so here it is two possible sites to phosphorylate. So I have S, which is the substrate, and then it gets together with an enzyme, and through an intermediate process, it eventually gets phosphorylated. So I get S phosphorylated and C the enzyme. But here there is an additional step. As I said, this phosphorylated substrate finds the enzyme again, and through another intermediate, it gets phosphorylated in a second place that I cannot see here. Oh yeah, this reaction. So it has two phosphate groups now. Yeah, and this network one can construct for an arbitrary number of phosphate sites. So this would be the two-site phosphorylation cycle. The one that I showed in the first tutorial was the one site. And then if one has a substrate that can get N phosphate groups, then it will be the N-site phosphorylation cycle. And then there are variations of this. But this is one well-known network. It has 10 complexes, 2 connected components. Then it has rank 6 and deficiency 2. And it tells me that then I should apply higher deficiency theory for this because it's not deficiency 0, not deficiency 1. So I will go to the higher deficiency report. No, maybe I'll go to the, yeah, maybe higher deficiency report. Let's see. Yeah, it already tell me that it has the capacity for multiple steady states. So this network is multistationary. So there is some rate constants, and it gives me the rate constant. So for these values of the case, it gives multiple steady states. So this is a tool that one can use to either find references or, yeah, check some conjectures, examples to build conjectures, this kind of stuff. And you can just download it for this webpage. I think it doesn't even need an installation or anything. Yeah, any questions so far?
This website is this is freely available.
Yes, you can just go to Finder. So I don't know if I can show you this. It is tricky with the sum.
Maybe for the online participant, it is better to place the link on the chat.
Yeah,
chat
maybe
box.
I will share this. Oh, okay, right.
The chat.
Yeah. Maybe I'll share it, but yeah, so let me find the chat. Here it is. Yeah, this is the web page, and you can find here Reaction Network Toolbox. You can download. It's very simple, and they keep updating it. So it does not have all the theory, but it has some. Can be very useful. So this is the first thing that I wanted to show you. Second thing. Now, I want to share my slides again. Yeah, so I suggest that maybe you try with the networks from the first tutorial, everything that we have done. But first thing is like, maybe try this tool and see what you can say with the existing tools. And what you cannot say, then that is the source of research. So these were the networks from the first tutorial. I will also maybe upload this file and then you have them. And my next suggestion is that you try all the concepts from the second lecture. So figure out if you can compute the stoichiometric subspace for these networks, if you can find conservation laws, if you can compute the deficiency for these networks. This is the second group of networks that I gave you. Some of them appeared yesterday in my lecture. And then after deciding whether you can compute the stoichiometric subspace and these notions, maybe you can decide whether for some of them you can use the deficiency theory that I showed in the third lecture or the injectivity theorem. And I remind you, if we know that a weakly reversible network has deficiency 0, then we know that this will be monostationary. So this is one thing that you can check. If some of these networks has deficiency 0 and it is weakly reversible, then you will know that it does not admit multiple steady states in a stoichiometric class. And the second one, just to see if you understood this other criterion, you can compute this matrix that was kind of parametrizing Jacobian matrix. And the question is, if there is no degenerate positive steady state for absolutely no k, and what is equivalent if this determinant does not vanish for no value of mu, so this mu should be in the intersection of the kernel of gamma the positive orthant, and this should be in the positive orthant of our n. So if for all possible values of mu there and lambda, this matrix is non-singular, then it means there is no degenerate steady state. And then the network will be injective. And then if it is injective, it will be monostationary. Injective is strong. So this is the third exercise I propose. So my plan was maybe to let you work a bit on this, but since I don't know how much time we will have, maybe I'll go with the other exercises and maybe do some of them with you, and then leave the rest of the time for you to try and ask questions if you have questions. So the next theorem to try would be the one about ACR that I mentioned. Still, any questions so far from the last things that I said? No questions here. So I wanted to go a little bit slower with these last two things because they were in yesterday's lecture, and I know it was a lot. So I first talked about this ACR condition. ACR meant that there is one of the variables that at steady state or positive steady state always takes the same value for fixed K. And I gave these two examples. And we know that the first one has ACR because we can somehow draw the steady state variety. And also we have this equation here, right? That is telling me XA always has this value. The second one does not have ACR for all values of K, but it will whenever the discriminant here vanishes. Just it will have like double root. And then it will be only one line. So the two lines will collapse into one. So this we know because we can understand those systems. But I gave you one necessary condition for this. And the necessary condition, to check the necessary condition, what one would need to do is to first construct this matrix here. I showed you in the lecture for this system, but I know it's big, so maybe we can do it for one of the smaller systems together. This was not a good idea. Okay. So maybe I do for the first network, since we have it. So the first network is A plus B goes to B. And then B goes to A. And I computed the stoichiometric matrix before. It was like this. And I know that one of these is redundant. So if I want to compute this matrix there, I need maybe I need the reduced version. So I can remove one linearly dependent block. I can choose, but maybe let's remove the second one. I have the matrix that encodes the reactants. And in the first column, then there is A and B. In the second column, there is only B. Sorry, I forgot here to write transpose. So if I am to compute this matrix, then I will need -1, 1. Here in the diagonal, I will need a 2-entry vector. And then the transpose of this one. So this is what it means.
And then I need to decide what goes in B, but B should be in the kernel of gamma. So how would any vector, I need to check the rank of this matrix for any vector in the kernel. So how can I write a vector, any vector in the kernel? Somebody was about to say something? How would you check that the rank of this matrix? So first of all, to be able to apply this criterion, I need that the rank of this matrix is the maximum. So it should be 1. Okay, let's maybe this 1, 1. 1, 1. You mean for the kernel? 1, 1? Well, I need all of them. So any multiple of 1, 1. So I would take B to be, for instance, A. So any multiple of 1, 1.
Yeah.
So then I would have minus A times 1, 1, 0, 1. And this is minus A 0. So this is a very simple matrix, but let's see what my criterion is telling me. To be able to apply this criterion, I needed some condition of non-degeneracy. So I needed to find one non-degenerate point in all irreducible components of the positive part of the variety. So all irreducible components of the variety that intersect the positive part. This is not so easy to check as it is, but this, as I told you, kind of parameterizes the Jacobian. There's only one thing missing, that is somehow scaling the columns. But for this criterion, this is enough. If I have full rank in this matrix, then I guarantee that absolutely no steady state is degenerate. So it's a stronger condition. But then if rank of this matrix is the maximal one, then I guarantee that the condition is satisfied. How can I guarantee that? Well, this happens for any A that is different than 1. I don't need to do anything. This is for free with this matrix. It's different with the bigger matrix, but here. So I told you that the 0 entries are a problem. And then I don't care so much about the 0 entries. Okay. So yes, outside of the 0 entries, this has rank 1. And then under this condition, the theorem I showed you yesterday told me that when I remove column I, in order to have ACR for variable I need the rank to drop. So which species is the candidate here for having ACR? Which column can I remove so that the rank drops? It's not a tricky question. Yeah, it is. So this matrix is really simple. In this case, it's obvious. If I remove the first column, then I have rank 0. So this would tell me that it is possible to have ACR for the first variable. But yeah, this is exactly what I have. So I have fixed value for the first variable. It does not guarantee that there is ACR, but it's a necessary condition. So what I know from this is that I cannot have ACR in the second variable. Okay, and I say it's not a necessary condition, and you will find out something if you try example 2. So maybe I leave you some time in the end to try it. So is the criterion understood? Now maybe I can show you the original example. I don't know if I can. So the big one that I did so fast yesterday. And maybe it makes more sense now. Yeah, this was the one that I showed yesterday, the bigger network. And here I had the stoichiometric metrics, but I had removed 2 rows already for you, 2 rows that are linearly dependent on the others. And I have my matrix B. And then what I need to use my criterion is to first find all elements in the kernel. And I can find a basis of the kernel. The kernel has dimension 3. So I can find 3 vectors in the kernel. This. And any vector in the kernel will be a linear combination of those. So I can plug in this vector in the diagonal matrix. And if I do the product of these times a diagonal matrix with these entries in the diagonal times transpose of this, I get this matrix. And then again, outside of the zeros, so if I plug in A1, A2, A3, 0, then there is a problem, or some of them. But outside of the zeros, this matrix in general will have rank 3. If I remove this, then it will always have rank 2. So is that now understood? Because yesterday I had the feeling that it was just too fast. If there is no question, I can move to the last criterion. And this has somehow the outcome of the other theorem that I showed yesterday. This was the theorem in which I was wondering about the dimension of the steady state varieties. And I show you a big theorem with a lot of technical conditions there, but let's see what it means. So regarding the dimension of the positive steady state varieties, I have 2 possible situations. I am assuming that my network has rank S. And then I remove n minus S linearly dependent rows of the matrix gamma. And I construct this smaller system, which has S rows. So I will call this function, vectorial function, G. And G depends on K, still. K is here. And now, what the theorem says is that there are 2 possible situations for a network. So for a network, meaning for the steady state varieties, for the family of steady state varieties, when I consider all the possible values of the case. And the 2 situations are the following. Either I have some K such that the corresponding steady state variety for that K has some point, let's say some positive point, with Jacobian having rank S, so non-singular Jacobian. So this would be a non-degenerate 0 of this function. So degenerate zeros, I said it somehow yesterday, waving my hands, but degenerate zeros are just the double zeros of a polynomial system, or so it would mean, double zeros or points in higher dimensional components or singular points. That's what would make the rank of the Jacobian drop, right? So either I can find one case such that there is some non-degenerate point in my steady state variety, or I cannot. So the other case would be for any K, any point is the generate. So if I can find one point, and there is a way here to check that, we'll go to that later. If I can find that, then this guarantees that for generic values of K, the dimension of the complex variety, but also the dimension of the positive part is given by the number of linearly dependent equations that I have. So the dimension is n minus s, codimension s. Well, as long as it's not empty, it could also be empty. So if the variety is not empty, then it will have dimension n minus s. If that happens, so if this happens, additionally, it means that the subset of K's for which this is non-empty is Zariski dense in R to the R. So I have sufficiently many values of K such that if I am making a mistake when estimating my case, I kind of can be sure that the behavior does not change. And if that happens, then for generic K also, all the points in the positive steady state variety are actually non-degenerate. It's not only that I have one point which is non-degenerate, but all of them are non-degenerate. This does not mean that there cannot be any some case for which there are some degenerate points. But for generic K, and generic K would mean in a Zariski dense subset of R to the R, the steady state variety, the positive part, even has dimension n minus s as expected. So it would behave as a linear system, and all points are non-degenerate. If this is not the case, if I cannot find a K with a non-degenerate point, then this means that the subset of Ks for which the steady state variety, the positive steady state variety, is non-empty, is very small. It's contained in a Zariski closed subset of R to the R. And for all of this case, the dimension of the steady state variety is larger than expected. And this actually means that all of the points are degenerate again, right? So this is the two possible situations. And then the good thing with this is that I can check by only checking this. And to check this, all we need to do is find a vector just as before. Find a vector in the intersection of the kernel of gamma with the positive orthant such that this matrix has maximal rank. If this is possible, then we are in this scenario. Otherwise, we are in this scenario. And then I propose that you try this check for these two networks. Is there any question?
Can you show the previous slide once again?
Yes.
Just go. Yeah. Okay.
So maybe I can show the computations for one of those networks in the remaining time because there's not so much time for working groups or anything. So you all have this network with you. This is the first network, sorry, the second network in the first tutorial. Or maybe I can do them here. Maybe I'll do them, the computations here. So the gamma here, first reaction, this is how I do it. I get 1x1 and nothing else. So it's 4 species. And the first reaction is just giving me 1x1. The second reaction on the way back is losing 1x1. So this would be my first reaction. This would be my second reaction. Then this is the first one, the third one. Then I would also get 1x1, but here I lose 1x2. Then for the fourth one, I lose 1x1, I lose 1x3, and I gain 1x4. And the fifth one is just the reverse, so I just need to change signs. Last reaction, I would get one of these two and lose x4. So this is the stoichiometric matrix. Now, I want a reduced version of this. What is the rank of this matrix?
It should be 3.
It would be 3. And actually, the last 2 rows are linearly dependent, so I can remove the last one, and that's it. So now I need my matrix B. And B, it just has the reactants. So the first reactant for the first reaction is just all zeros. And on the way back, it has 1x1. For the third, I have 1, 1, 0, 0. Fourth is 1, 0, 1, 0. Then the fifth one only has x4. And x4 is also the only species in the last reaction. So this would be B. Now, so this is different from the previous criterion. To be able to check this condition, I only need to find one element in the kernel such that the matrix gamma prime diagonal W B transpose has maximal rank, in this case 3. And yeah, again, you can parameterize the vectors in the kernel. Here you would also have 3 parameters because it has dimension 3. But I don't think we have time for that, so I will give you one element in the kernel. This element is in the kernel of gamma. And if I write this matrix, it gives rank 3. So it does satisfy this. And then I am in the first situation. So now we know that this network for generic case, well, has either an empty positive steady state variety or dimension. So we have 3 equations, 1 variable, dimension 1 steady state variety, and even positive steady state variety. And we know that for most of the case for which it is non-empty, then all the points are non-degenerate. So now I leave you this other network to try. Maybe I stop here, and if you have questions or if you tried some of the things that I proposed, you can ask me. Otherwise, you can also reach me by email anytime.
Thank you. Let's clap for Beatriz for And thank you very much for introducing this toolbox. I think this is going to be really very interesting for the participant. I was just curious about this kind of study from the chemistry point of view. People are, this is called the abstract study of the chemical network, or in chemistry, people are interested to see the real reactions. And what is the interest for chemistry from the chemistry perspective?
So as far as I know, it's mostly biochemistry that is making use of this. Apparently, biochemical reaction networks are kind of special within chemical reaction networks. And I cannot tell you much, but I know some people who are collaborating with biochemists, and I do have some colleagues who are biologists. And yeah, we have some projects where they try to build a model, they test in the lab, and if it does not fit, then they ask me, like, how could we change maybe the network? Would that make sense mathematically? What would we expect? And then they test and so on. So there are some people who are trying to use it. I don't know how.
Because in your lecture you were trying to cover the whole aspects. Yeah, the conservation was there as well, and maybe and similarly the almost all the tools what they are concerned regarding to a chemical reaction. So everything it was there. So I was just curious whether this abstract study is.
There is much more, actually. I only could give a few initial definitions. So if anybody is interested in this topic, then they should read some of the references that I gave, because they will find very soon concepts that were not.
So are there any questions from the audience side? Thank you, Beatriz, for the answers. Anyone else with any comments or questions? Maybe from Karachi or online participant? Fazil, would you like to say something? Okay, if this is the case, let us thank Beatriz once again. Thank you, Beatriz. Thank you very much. Time for 2 weeks
That's a
to
great
and
experience.
Carlos. Yeah. And coming to Pakistan, and I hope you had a wonderful stay here at Lams, as well as you are enjoying your stay in Karachi. And we hope that this visit is really paid off. And let me just tell you that in Lams, there are some colleagues who are working in applied side, and they followed your lecture, and probably the persons who are working in the dynamical system, so their interests are completely different. So they are trying to understand this matrices algebra structure, how it can be useful for their study, abstract study of the dynamical system from their tools. So I don't know, maybe some new species or some new kind of mathematics can evolve through this particular interaction. But
That would be great.
definitely, yeah, but definitely a lot of interest is there from the algebraic side. And thank you very much once again for introducing this subject. Thank you.